All right, so today we are talking about active data selection and information seeking by Thomas Parr, Carl Friston, and Peter Zeidman. So, Bayesian inference usually focuses on two issues. The first is estimating parameters of some model from the data, and the second is quantifying the evidence for alternative hypotheses. We're going to be doing neither of these. This is going to be about a third issue. There's going to be a ton of data. There's going to be more data than you can realistically sift through. What data do you choose to look at in order to improve your model as much as possible? What are you actually going to focus on your weak spots? And this is going to allow us to be much more computationally efficient, as well as make the most of the data that we have by picking the important data that we want to focus on. There's going to be some information content in the data, and we are going to try to predict that. We are going to try to say, okay, what is the most important data in front of us in order to learn how to solve the problem that we have been given? And that's the core concept. So the hook for this, the analogy that we're going to use, is that of vision. So we have the entire visual field that we're looking at right now, you and I. And we're not going to use the entire thing. We are going to focus on one tiny spot in order to pay attention to that thing. We are naturally paying attention to the thing that we think is the most interesting. And this is going to be the analogy between the thing that we naturally find interesting and the information content of the data available to our models. We can, of course, look to active inference, which is going to say that we are expecting some observation and the world is going to do something. And we want to minimize the energy between these two things. And this minimization of energy is what we want to maximize. We want to learn as much as possible. And this is going to be maximizing the information from it. So we have a lot of data, and it looks like data isn't getting any smaller. So we want to be as efficient as possible in order to improve our model. Let's jump into what the model is actually going to look like, and that's going to be this Bayesian bit right here, as well as figure 1. There's going to be some data y that you observe, and then there's going to be some belief about the causes of this, which we are going to say is the distribution of some parameters theta of our model. There's going to be the likelihood, which is the distribution of the data based on our parameters from the observed data, and the posterior, which is the distribution of our parameters based on what we've seen. So we can see that right down here, to where there's going to be some data that we observe, and based on what we perceive, there's going to be some parameterization trying to describe what it is that we saw. And this is going to be the model right here. And this is going to feed into how we start to improve the model. So we have this thing right here that we want to improve. So we're going to have some data sampling. It's going to be a big circle that leads into itself. So we get that, we improve the model, and based on the improvements of the model, we decide what we want to look at next. The core framework is going to be that right there, and we are going to focus on how to select the data that is going to help us as much as possible. So we have that section 1 right here, which is going to be this overview, which is saying that we want to select the data carefully. And then let's just go over what the next few sections are going to be. There's going to be section 2, which is going to be the mathematics of Bayesian inference. Section 3 is going to be a very simple worked example. Section 4 is a little bit more complicated of an example. Section 5 introduces time. Then section 6 is going to be the more complicated example, a clinical trial application, where we are flooded with information and we want to make the best decision as soon as possible in the most efficient way. And then discussion and conclusions. And that is going to be the basic layout, which is going to lead us into section 2. All right, so essentially what we're going to be doing is building, based on Bayes' theorem, the Bayesian learning scheme that we're going to be working with, which we're going to call the generative model. We have some distribution of how our data is created based on the parameters, and the distribution of those parameters, our priors on the parameters. I think this is just the prior and the likelihood coming together to build the posterior, as well as the distribution of the data itself that we're going to be seeing. This data itself is going to be called the marginal likelihood, and is going to be built of the expectation based on the parameter distribution on the probability of getting y based on your parameters theta. So what we're going to do is we want to build up the information idea, which is going to be in active inference, the idea of the energy. There's going to be some prediction of the model, and there's going to be some activation, or there's going to be some observation in the real world. And you want to measure, like, what's the difference between those? And the information content is going to be a measure between those two things. And those two things are going to be probability distributions. And of course, we are going to take the KL divergence between the two. So the generalized information is the expectation of the y based on this pi. Pi is going to be our policy. The policy is for selecting the data. Essentially, we do have to choose the data at some point, and the policy is going to choose it. So that's what we're going to be looking at. So this is the probability that you get some data based on your policy of data selection for the KL divergence between these two things. And so that is going to be the information gain, and this is also going to be equal to this information based on your policy pi of the KL divergence between your probability of your data as well as your parameters based on your policy selection compared to the distance between the two individual things based on the policy pi. That's going to be the mutual information between y and theta, or most importantly, the thing that we're actually going to be using is the conditional and predictive entropy coming together to form the information content. And this is essentially going to be saying that you have the conditional entropy. You know the rules. You have a 90-10 coin, and you know that you have a 90-10 coin, some kind of bent coin. How often can you correctly call what's going to happen? And so we kind of want to minimize this conditional entropy. This is the negative of it, of course. We want to minimize this thing. But then there's the predictive entropy. And predictive entropy, as I understand it, is saying that you need to learn the rules. You need to figure out exactly what you're looking at for this 90-10 coin. You need to learn that probability distribution so you can know how accurately you can actually get in there. This conditional entropy, that's a barrier we're probably not going to be able to get over. Once you know the rules, you know the rules. You have to work within that. But learning the rules themselves, that's where the key is going to come in. That's where the interesting thing is going to step in, because that's how we actually figure out exactly what the spread is based off of our parameters theta. And so we're just going to remap this to be a slightly different thing. But this slightly different thing, we have these nested expectations. Do you see? And these nested expectations are going to be the motivation for going to a graph, learning scheme. We're going to stab these into a factor graph, and that factor graph here, let me just show you visually. These we're going to talk about here in just a second. But what we're doing is down in section 3, we are cutting ahead. We are taking this Bayesian network right here, this top left, and we are moving into the factor graph. So we can move into the Forney factor graph so we can talk about message passing. So for section 2, we are going to be talking about these things on the top right here. So that's what this is going to be. This information content right here, this is going to be the exact same thing as what we see right here, but mapped into a slightly different way of talking about it. It is going to be moved into the notation of parents as well as children, of the messages and the information flow. So what we're going to see is we're going to see this lambda right here. I think it's a lambda. It might not be a lambda. I think it's a lambda. This lambda operator is going to either be summation or integration, but we're just going to call it summation because we're dealing with computers. It's all going to be discrete. It's all going to be digital. And so that is going to be some summation, and that is just the summation of everything around it. Now, in general, whenever we talk about the explanation for these things, we're only going to be talking about one message to one parameter to one thing in these simple examples. So you can kind of ignore it for now. It's important to keep in mind, but we're only going to be focusing on the idea of having one message towards one parameter for the explanation specifically. So you can see that it is going to be the message for the ith parameter being passed to the ith parent from this, and then the entropy of the message of the child, the information content of this right here, minus the thing for the parent. So we are going to have the message being scaled by the information content of the, is that right information? It's just a message. The information of the message compared to its entropy of the children being scaled by just the part for the parents. And here you see the definition for these things right here, where the information being sent to the parents is going to be how we update our parameters, and the information being sent to the children is how we actually generate the data. So this is going to kind of be reminiscent of the circle that we just saw above in section 1. And this is, well, I mean, it's not, you don't really understand this at an immediate glance. You kind of have to stare at this for a while to really make sense of it. But this information passing scheme is the exact same thing that we just talked about a second ago, but it makes it to where we can put it into a factor graph so we can manipulate it into message passing so that we can actually start to figure out exactly how we are empirically going to discover this information content right here. And that is the idea of what we're doing for section 2, leading us into section 3. All right, so working the example. Remember, we are going to have the data choice for the policy pi. We are going to have the parameters theta and the data y. And so we're going to use this Bayesian network to actually build up our factor graph. And the way that we're going to do this so that it's more tractable is that everything's going to be a normal distribution. The data itself is going to be actually I can show you this, but I can also just show you this right here. This is going to be the important part. And this is a great way to visualize it. Let's look at the left side right over here. And we're going to see that whenever you have, it's a cosine, of course, a cosine of the policy pi, which is confusing because as we talk about this, I'm just going to call half right here. And we're just going to remember that there's some multiple of pi's in there, the number pi and not the policy pi. I'm going to avoid talking about the number pi. So whenever we're right here at 0, you can tell that you can easily discriminate between these variables. If they weren't color-coded, you could still kind of tell like, oh yeah, these lines are going here. And that's going to be high information content. You can look there and you can learn a lot about your variables because you've split it up in a smart way. And you see the exact same things whenever we get to the extremes. Those are just negatives. But whenever we're right here, right around this halfway point, then you have no idea what's going on. The information content down here is going to be really low because you can't tell what's happening. So you need to modify it to where you are going to be choosing your pi based on where the highest information is. And so that's going to be the main relationship there. And the way that we actually do that is that we have this Bayesian network that we just built up. And then we're going to be using all of the parent as well as the child messages that we were talking about earlier to build the factor graph. We're going to move into a Forney factor graph, which just makes message passing start to be a little bit easier. The main difference is now variables are going to be represented as edges instead of them being represented by these circles here. It is going to be a little bit more technical than that, but this paper actually doesn't really say that much about it. It does say, is it up here? Yeah, then we move to a normal Forney factor graph given by 25. And so we don't say a whole lot about that. That's going to be not so important. We're going to check that out in the MATLAB whenever or whatever code it is going to be in the next video. And we're going to move to this message passing thing. And this message passing is going to allow us to talk about the conditional and predictive entropy that we did see earlier. You can see that these are different messages. We'll get into that in just a second. These are just the specific messages that we see talking about the parent and the child, but remapped into this idea right here. Because you can see these distributions right here are exactly what we saw right here. The probability of y, given our theta and pi, probability of y, these are going to be the messages that we send to the parents and the child. And you can see those right over here. Cool. So with that, we see that we have these normal distributions and we are going to move there using these right here. Now, if you work out, it is going crazy with the highlighting right now. I'm just going to avoid doing that. If you actually work out what the messages are based on equations 4, the top line of 3 and the bottom line of 2, you are going to get these right here in order to figure out what your messages are actually going to be composed of, and you can plug in the actual information content in order to get that. Now, I'm kind of just taking their word that this math works out because I did not calculate it on my own. So we are going to be able to figure out exactly what the Bayesian network was, define what our prior and our likelihood are going to be, and from there, plug and chug based on what we saw right there in order to calculate what the actual message passing graph is going to be composed of. And that is going to be these messages right here. From there, we can plug it into the conditional and predictive entropy that we just saw before, where the conditional entropy is going to be the thing that we're trying to minimize. So we make it a negative. It's already a negative, so it becomes a positive. And we're trying to maximize the predictive entropy, so it stays its same sign, and we see that it's going to be a negative still. And that, whenever we plug those things in, we are going to see that that builds up our information landscape in this little two-dimensional thing, but that's 2 dimensions with pi. So that is going to describe how we are going to define our information to maximize how we can update our knowledge about our parameters theta in order to keep moving through. And that is going to be the main idea. And so you can also see we calculated the information if we have some normal distributions for equation 4, but you don't have to use normal distributions. Here's some other priors that you can use instead of that in order to get these generalized expected information gains based on the shape of these things. And that is going to lead us into 4. For section 4, we are going to describe our generative model like this, to where we are going to have the probability of our data as well as our parameters based on our policy selection pi, which is going to be composed of our likelihood times our prior, where these are both going to be normal distributions. The main thing that is going to be contributed here whenever we're doing this function approximation is the idea of phi, which is going to be our basis functions for mapping the parameter space to the data space, which is cool because it's completely interpretable. Here's how you do it. And so this is going to be a Gaussian radial set of basis functions, which are nice because they are mathematically tractable, they're pretty straightforward to work with, and they work well. So what we're going to see is that for the likelihood as well as the prior, these are going to be normal distributions with a mean of eta sub theta and sigma sub theta, or a mean of the parameter itself cast into data space by our basis functions, because we are looking at the likelihood, which is talking about y, and the variance of sigma sub y. We're also going to have the expectation of the data based on our parameter and our policy selection to simply be the summation of the parameters multiplied by this basis function with the subscript of pi. And that's basically going to mean that we are talking about whenever you select the basis functions based on your data selection for pi. So the thing that maps the data to the parameter space is going to be modulated by the policy selection, by the data selection pi. And that is how we are going to define how we take the expectation right here. So scrolling down a little bit, we're going to see that we have the posterior, this posterior right here, which is going to be, of course, a normal distribution because it is the composition of 2 normal distributions. And we're going to have the data based on the policy pi also being a normal distribution. These are going to be modulated by this weird-looking gamma thing with the subscript of pi, which is going to be defined as the variance between the data itself and the variance of the parameters. It's going to be the inverse of these, and essentially we are just going to cast this into the parameter space so that everything is speaking in the same language, and then we're going to take the inverse of it. So we're going to see that that is going to modulate exactly what is going on right here. It is going to be the variance. This is the sum of 2 variances, which is going to be the variance of the posterior. And we are going to multiply this by the mean as well. And the mean is just going to be the mean of the parameters divided by the mean of the variance. And the same thing for the data, except for instead of the mean, you're just taking the data. And you still have to transfer it from data space into parameter space. And that's going to be what we're looking at for these right here. And this is going to define the posterior, which is going to be our update rule. We are going to use that update rule in order to plug this into a little toy data set that we have in order to actually go in and approximate the function. So what we're going to do is we're going to have these parameters pi. These are going to have some mean and some variance each, and the policy selection pi. Here, it's just going to be completely random. It is just function approximation where the policy is just random selection. And as you can see, it does a pretty good job. Here's the posterior modes right here, which is, of course, based on the posterior that we were dealing with right there for the update rules, which is going to talk about the mean and the variance for them. Or I think so, yeah, that's what it's going to talk about. And these are going to be the choices. And you can see from the red circles that the random choice sometimes made the decision to sample something that you already had a pretty good grasp on. You're kind of wasting your computation by doing the same thing twice. And it makes it to where like you're very certain for that parameter. But overall, you could do a lot better if you measured based on the information of what you were dealing with, which is exactly what we're going to see here. So based on the generative model that we just pitched a second ago, we are going to get this information content out of it. And that simply means that the posterior modes, that's actually going to be plugged in order to, based on the information content, figure out what our policy is going to be. And this is just going to be measured by multiplied by some constant, then you're going to have the information content right there. It's just some basic of comparison like that. So suddenly, you plug in all of your parameters with their means and their variances. You multiply it by this phi, which of course maps the parameter space to the data space. Multiply it by your parameters, add some noise, and then you can go from your sample to your prediction right here. And this is going to talk about each parameter, theta, as you go along. And you can see that your choice to update those parameters is going to be much more spread out. You're going to have a much better spread of how you actually update because you chose where to sample your data in order to maximize the ability of the generative model to predict the function. We're also going to have the idea that you don't need to run every single thing. We want to have some early stopping. So if your information content is going to be below some object, if you're not getting a lot of information out of what you're doing, you're just allowed to stop. You're allowed to say, okay, now it's good enough. And whenever we do that, we are going to see that we have the exact same thing, except now we have this G. This G means that we have early stopping if we want it. So the difference is we're going to make a lot fewer choices because even though the mean and variance is going to be a little bit worse right here compared to what we saw earlier, or I guess you have to eyeball it, what we know is that this is good enough. We did a good enough job and we made enough choices to where we are no longer getting so much information out of what we're looking at. So we're able to stop. For the last one, what we're going to do is we're going to change the data up. Now the data is different. And there is a massive amount of variance on the left and the right, but you have this little tight section right here about 0. And whenever you do that, you can see that there's a massive amount of prediction. And this is going to be our conditional entropy, to where it's saying that it doesn't matter how much you sample over here, your variance isn't going to go down. The variance is just massive in this data set. This is as good as you can get it. So what we're going to do is, well, what the model is going to do is recognize that, okay, we can only really work in this little tiny space right here to make it better. Other than that, there's not a lot of improvements that we can make. So we're going to try to make it good right there, and then we're going to stop because this is as good as it gets. It's not great, but this is as good as it gets. And that is the idea of how you are going to do this Bayesian updating rule in order to do some function updating, some function approximation. Moving down to section 5, what we're going to do is consider processes that evolve through time. So we're going to have the data, and we're still going to have our phi, which is going to, of course, map the data to the parameter space. But now we just have this time evolution space, which is going to just be an outer product between this basis function that we've been dealing with and just this time dimension. That is the only major change that we are going to implement in order to have time. And so it's not too different whatsoever from what we were seeing before. It's a little bit more complicated because now we have two different spaces. We have this larger outer product space that we have to deal with. But other than that, it's exactly what we just saw. As we scroll down, what we see is the exact same thing that we just dealt with, except now we have time evolution as it shifts down. And we also have this new phi sub tau right here, which represents how to move to the next time step. And that is the only real difference that we have to deal with. So as we can see, the posterior is slowly going to update as it experiences more data and as it experiences more time, so it has actually a place to update through choices of our parameter pi. But other than that, it is quite similar. We're just dealing with an additional space. Throwing in additional spaces does not make it too much more mathematically complex, although it does make the space of which our means can be very large. But that's totally fine. And that is all that we really need to talk about for section 5, moving on to section 6. For section 6, we are going to be looking at a clinical trial, or at least a toy clinical trial. In the 2014 West African Ebola outbreak, a key argument was made to rapidly develop epidemiology and the active study to efficiently compare several possible treatments and figure out what was the best one and adapt as new information emerges, not after the study, but like during the study, so that you can actively, during the study, stop a treatment arm, reallocate participants to different groups, or do whatever you need to maximize the probability of survival. And so what we're going to do is create a toy study, which looks at a similar thing. So what we're going to have is going to be the probability of the data, which the data is going to be the survival, based on our parameters. Some set V, which is going to be the allocation between the placebo or the treatment group, the demographic, which is going to be male or female, and then the policy pi. And this policy pi is going to be pi sub t, which is going to be survival rate as time goes on, and like who you should be sampling and stuff like that. This is going to be the categorical variable. These are actually these two are going to be categorical variables, as well as the data. This is going to be survival, survives versus not survives. The demographic is going to be 50-50 male-female split. The demographic is going to be chosen by the allocation group to where you decide how to allocate between placebo and treatment. And then there's going to be the parameters, which is going to be based off of a normal distribution. And you can see that this is a little bit more complicated. We have a couple more things that we've tossed in. These are going to be categorical variables, which we haven't dealt with before. But this is very, very similar to what we just saw. This is just 1 degree more complicated because we're adding in a couple of new things. Now, because we added in these categorical variables, it's going to be a lot harder to analytically solve for what we're trying to do. So we are going to use variational Laplace in order to approximate what our posterior is going to be, for posterior estimates. And so that's going to be this right here, which I'll go over the math later, not in this video, but sometime later. It's just going to be variational Laplace, and we're going to calculate some Hessian. I don't think the mathematics is the most important thing to focus on right now. The more important thing is to understand how this is a slightly more complicated study than the 2 things that we just saw earlier. So we are going to have that. We're going to have the optimization scheme mapped out right here. And then we're going to have the information metric right here. And then we're going to figure out the message passing that we have dealt with, just like we did before. And that's really about it, isn't it? And we can jump right in to figure out what's going on. And so the first thing we're going to see is random sampling. And the sampling is going to be based on this pi sub r, this randomization ratio, deciding who goes into the treatment, which is going to be t, and who goes into the placebo, which is going to be f. We are going to find through the study that the treatment is actually harmful. You can see in blue here, if you receive the treatment, your probability of survival goes down, especially as time goes on to the right. And the time is just, you're randomly going to decide for each participant to check in on them once. And so you have to choose when you want to check in on them. And that's what this is going to represent right here. The volume of people that you decide to sample from at what time in order to check for survival. Sooner is good, but also because if you check sooner, you get to find out if they are surviving and you just have that information faster. But if you wait longer, then you are prioritizing longer survival times, where ideally there is a very long survival time to where this illness will not affect long-term survival rates. And as we look at it, the important thing to look at is going to be down here in the treatment group. This is going to be directly the allocation of the pi sub r for exactly who gets put into the placebo group versus the treatment group. what we're looking for is going to be very high placebo bars and very low treatment bars. And you can see here that it's not quite equal. It is pushing towards this right here, pushing towards having more people in the placebo, because this raises your chance for survival. But as we go down, we're going to see that in the intelligent sampling, it's much steeper curves here. Of course, there's no numbers. I don't have proof of this. I've just been eyeballing it. I hope you see it too. That this is going to be a steeper curve for the treatment to where it learns faster that it's dangerous, based on the sampling that you've done to see the probability of survival here as you continue your time steps going to the right. And you can see that right here as well for the posterior mode for the survival rate. If you were in the treatment group, you could see that survival tends downwards. And, well, of course, you can see it here too, to where the blue line is lower. But more importantly, whenever you have the intelligent sampling, it pushes a little bit more towards having more people into the placebo group than into the treatment group. And you can see there's still a bit of curvature because you're just increasing in numbers. So no matter what, you're going to grow, but there's going to be some ratio of allocation. But for the third and final image, what we're going to do is we're going to show that we're interested. Wow, this highlighting is terrible. We are interested in longer follow-up times. And so we are going to have a bias. You can see it here. There's a bias towards longer survival times, to where we are sampling farther into it, farther into the study to maximize how much we know about, and also maximize the chance for survival as we go on. And you can see at the bottom right here, there is a much bigger bias towards putting people into the placebo group, because this is what actually maximizes your probability of long-term survival. So we were able to put a bias into the system for long-term survival based on how we chose to sample, just a bias that you can enter into it like any other bias that you enter. And that is going to reward us with what we were looking for. And that's awesome. And that is also essentially going to be the entirety of section 6, as we show that this is going to be the same thing that we were looking at, just a little bit more complicated with a few more variables tossed in. And that will lead us into section 7. For this section, what we're going to be saying is the same things we've been saying the entire paper. What we did, that was the key in this paper, was demonstrate that using information objectives, we can optimize data selection. And this is going to minimize uncertainty while still considering the cost of data acquisition. And it's going to balance the computational demands with model accuracy. So one thing that we're going to compare here is the maximum entropy sampling. And this would be about the same as this maximum entropy, this method that we introduced, except that, where is it? It's right here. We can have variance that is inhomogeneous. So if you have a strange variance curve that is not consistent throughout the entire data set, this method that we introduced in this paper can deal with it. And that is going to be one key change. So there's going to be 3 areas for advancement that we're going to talk about. Here we go. Several technical points. The refinement of the active data selection process, the evaluation versus alternative sampling methods, and identifying the appropriate cost functions. So for the first, from choice 1, essentially, we're going to need more sophisticated recursive planning. And of course, it's recursive. Everything is recursive these days. And we need to figure out how to handle these sequential dependencies in order to improve the decision-making frameworks. For point 2, which is going to be the second paragraph here for the empirical evaluation, we need validation sets. We're going to need something that can actually be small enough for humans or some other intelligent mechanism to go through, but still to a good size to where we can generally sample about how we're doing whenever it comes to, okay, so we have this information metric. Is it actually working? How does it actually empirically function as we go through and apply it? And then for number 3, which is going to be the the cost function development. I was highlighting the wrong one. That's going to be down here for the third one. The question is the challenge of balancing multiple objectives and understanding context-specific solutions in order to maximize what it is that we actually want. Cost functions are just a nightmare to actually deal with. As soon as you say you want one thing, you realize that it's all context dependent. You don't just want one thing, you want a myriad of things. However, whenever you're actually figuring out, okay, what do we exactly want, you have to write something down. Just like before, whenever we said we want to just focus on survival, there's a lot more to just survival than your heart beating. There's a lot of questions of happiness of living and quality of life that go into the problem, even though our simplistic cost function was just trying to maximize the probability of survival. From there, we can jump into conclusions, which is actually like one paragraph. So we had the biological parallel between the visual system and efficient sampling, because we want more efficient sampling inside of what we're doing. There's the practical implementation for the foveal-like methods that we use to sample and the cost-aware data selection. There's the healthcare applications, like the clinical trial that we applied. And then there's going to be the future relevance, which is that datasets are not getting smaller. They're only going to get bigger. And the cost, like the power needed to actually train these neural networks or active inference agents that we've been dealing with so far, that power requirement is only going to grow. We need to be as efficient as possible. We need to recognize that the cost is very real. The power needed to run these computers is very real, and the computation is something that we need to minimize as much as possible in this era of large data sets and energy-hungry models. And that is a brief overview of this paper. I hope you learned something from it. I really recommend that you go out and try to read it. I'm going to have the link for the paper in the description. And thanks so much.